All right, we'll continue with our establishment of the matrix vector weak form. Before we sort of plunge onward, I should just clarify some notation. So I know I used the following symbol. I've been using this symbol. I probably said what it means, but let me make completely clear. This symbol is since or because. Right? I realize it may be slightly archaic notation that has fallen by the wayside, but I tend to use it still. Okay, so that's where we are. Let's continue then with the matrix vector form. What we did in the previous segment was write out the important contributions that arise from the weak form for a general element, right? And we consider the two main integrals that arise in the weak form from the integral that remains on the left hand side, as well as the one that the one on the left hand side which comes from the stress, and the integral that's on the right hand side that arises from the forcing function. We wrote these out for general elements. What I'd like to do now is take the step of just sort of particularizing them for the first element, right? Because of the fact that it has that Dirichlet boundary condition. Okay, so note that for E equals 1, okay, we have integral over omega E WH comma X sigma H A dx. This is simply C2E multiplying E A over HE, right, times, let me see, how does it work out now, right, correct, this times minus 1, 1, D1E, D2E. Okay, right, and you can actually see this in a very simple manner by just taking the general expression for a general element E and recognizing that C1E is not present in the expansion for element 1. All right. Likewise, we get integral over omega E WH F A dx equals, in this case, it's just a scalar, right? In fact, well, actually, all the integrals do turn out to be scalars when we complete the matrix vector products, okay? But in this case, we don't even need to use matrices and vectors. So the forcing term is just C2E. We have F A HE divided by 2 times 1. Okay, so those are the contributions from element E equals 1. All right, what we are aiming to do now is pull everything together. We are going to use the same approach as we used in going from summations over the degrees of freedom for each element integral, except that we are going to now apply that idea to the sum over elements. Okay, and in doing so, we are talking of the following of the following complete weak form. Okay, so yet again recall the finite dimensional weak form. It's this: sum over E integral over omega E WH comma x sigma H A dx equals sum over E integral over omega E WH F A dx plus, let's not forget this term that we have not had to worry about for quite a while, right? The term coming from the Neumann boundary condition. So what we spent our time in doing over the last segment was expressing these integrals, right, in a more compact form using matrices and vectors. So what we now have is the following. We have the term above implies a sum over E, sum over all the elements. Now, for the general case, we have a form which involves a matrix vector product. So actually, let me do one thing. Let me first write out the contribution for element 1, okay, the special contribution for element 1. For element 1, we have C to E, but E is 1 for element 1. Okay, E, A, H, E, but that's H1. Okay, times minus 1, 1, multiplying the vector D1, 1, D2, 1. Okay, and recall that when we write D1, 1 and D2, 1, the superscript there refers to the degree of freedom for that element, and the subscript refers to the element number, right? So this is the contribution from the first element to this integral, right, to this integral. Okay, for the other elements now we have the sum E equals 2 to NEL, okay, of C1E, C2E, E A over HE times this very simple matrix 1 minus 1 minus 1 1 multiplying D1E D2E. Okay, so those two contributions, the special contribution from element 1 and the contribution from that sum E going from 2 to NEL, give us that integral that shows up on the left hand side involving the stress, okay, the stress and the gradient of the weighting function. Now this is equal to all the right hand side terms, and the right hand side terms also I can write as follows, right? Again, as we did for the integral on the left hand side, I will first write the contribution from element 1. That contribution is C2 for element 1 times F A H1 over 2, where the H1 reminds us that that is element 1, plus a summation E equals 2 to number of elements Okay, and that summation then is okay. That summation gives us C1e, C2e, F A H E over 2. Okay, all right. We get this contribution, and let me see, do we, oh sorry, we have F A H E over 2, and we have F A H E over 2 again, right? Okay, there we go. That's complete. Now, the terms we've written on the right-hand side are the ones that arise from that integral. Okay? And the term that we could safely not have to worry about when we were writing out these matrix vector contributions is that one, because that appears only at a single point. It just appears at the point on which we have a Neumann boundary condition. Okay? Now, we recognize that that term alone, WH at L, has a very specific, very simple representation. Can you think of what it is? It is C2 for the very last element, E equals N EL. Okay? So, the term that we add on here is C2 for the very last element times the data T, which is the Neumann condition on the traction, times the area. Okay? This is it, really. This is a nice compact representation of our finite dimensional weak form. This is everything. One thing that may be useful for me to point out here is related to why we get this simple representation. Okay? It's a fairly straightforward thing, and it's something that you may all already have noticed, but it's useful to point it out. Okay? So, remark. And this remark goes all the way back to our representation of UH in an element as being the sum of NA. Let me write NA as a function, expressed as a function of parameterized by XC, times DAE, and also to the corresponding representation for the weighting function. Sum over B, NB, C, C, B, E. All right. Of course, it's implied here that X is, though I've written this on the left-hand side as X, it's really X parameterized by XC. Right, and the same thing here. The same thing here as well. Okay, so now observe that, so this is of course for a general element which is written as, which can be depicted as this. We would have omega E. Here we would have X E. We would have X E plus 1. Those would be the global node numbers, right? And we recall that this comes from a bi-unit domain, which is -1 to 1, and that is 0. This is omega C. right, in the one-dimensional space parameterized by C. Okay, now, okay, so we have this picture, and what I'm going to use it to do is to ask ourselves what form these expansions take for UH and WH if we choose to evaluate these quantities, these fields, at the nodes themselves.